I wanted to just highlight some of these graphics concepts using some VTK.js examples. Now, obviously, we can't go into intricate detail on every graphics algorithm. We just can't fit that into a course on computer-aided surgery. So far we've covered what is surface registration and surface visualization and volume visualization. And we've covered on these notes the fact that, there are very low-level APIs where you literally have to describe every single triangle, and there's high-level APIs which relieve you of most of that detail. So for anyone doing computer-aided surgery, I would very much recommend that they were doing certainly their prototyping and proof of concepts and their research using a high-level API. It's only if you're really building a product for a commercial company where the thing has to run as fast as possible or as efficiently as possible for some reason, or maybe with a dependency on as few libraries as possible, that I would consider writing something in a sort of native low-level language. The alternative, possibly, if you want real performance, is to look at a games engine. The reason that's important is really because if you just look at the amount of money that's invested in them, games engines have to run as absolutely fast as a machine can run. And there's a lot of money in the industry, therefore they will have very highly optimized graphics. But normally in computer-aided surgery, we're not on the cutting edge of graphics. We're still trying to make these things work. The problem is, can your system work in surgery? Not really whether or not you've got the fastest graphics engine, much as I would like to spend time looking at graphics engines. So for the sake of it, we've just got to choose a middle ground, the middle ground today being VTK. It's popular, it's all open source. Documentation causes challenges for a few people, but then for those people that complain about documentation, you could always contribute documentation, it's open source. So stepping through some of these examples now, I've provided links to the JavaScript examples and the C++ and Python examples. Hopefully you can see my mouse pointer. So in this small example here is just really a cone to illustrate the fact that stuff gets rendered as triangles. So if I switch to wireframe, you can see where these triangles are. So in this case, it's a very small number of triangles, so clearly my graphics card can render these. So really, all of everything that you'd see in a sort of surface-based registration, and this includes many computer games, they are all underneath just lots and lots and lots of triangles of different colors. Now in terms of computer-aided surgery, when you draw things on the screen like diffusion tractography, the streamlines are generated as points or lines, but they're often wrapped in a cylinder, and a cylinder is generated just by loads and loads of rectangles, each of which is generated by triangles. I hope you get the point that with essentially points, lines and triangles, you can pretty much draw whatever you want. The question is, how do you generate that data? So for medical imaging, what was a really sort of crucial or pivotal moment was the marching cubes algorithm. So here we have an example which we can then run in our browser. So if you imagine this was a CT scan, typically in a CT scan, skin is quite a low intensity and bone is much higher. So you can pretty much do an automatic segmentation in this scenario just by selecting a threshold. At least it gives you something to be going with. For the phantoms, and like the pelvis phantom we saw in earlier lectures, obviously a phantom in thin air, just one ISO value is enough to extract it. So here we see a small demonstration. If I set a low value, the marching cubes algorithm is essentially searching through that volume of data, and it finds where the grey level intensity crosses that threshold, and it renders a surface. The surface, therefore, is determined by one parameter, the intensity value in the CT data that you're looking for. We can see also, interestingly, that obviously many triangles, my graphics card can render it quickly, but also it's a very efficient algorithm. We can actually recompute it on the fly, at least for this size data. If your data is massive, it will grind to a halt. And there are plenty of papers out there on how to generate these triangles in real time on a GPU. So these days we can do pretty much rendering and remeshing in real time. A point to note here though, when we think of an isosurface, you always think of the external surface. But the Marching Cubes algorithm has no idea whether something is an external surface or an internal surface. So if this voxel here crosses the threshold that you're looking for, you get a triangle. But similarly, there'll be surfaces or places inside that volume which also cross that threshold, and you end up with extra triangles. So if you wanted to generate an isosurface just of the skin contour, you'd often have to do things like internally fill the sort of basically the other grey values which you don't want converted into a surface. So it's not always entirely trivial. But you could do that with a sort of flood filling, segmentation tool, or a region growing thing, just to essentially block out in the insides of this so you don't get triangles in the way. So essentially the next question is, well, how does this work? But before I do that, here's another example. Imagine I've got a volume of data, and in the middle of that volume is 0, and on the outside, the edge of that cube, I go from 0 to 100. You can kind of see the idea that as I change my intensity value, again, what you're doing is you're finding that surface position within that volume. Just a point of note here, as I'm on the screen anyway, hopefully you can see, if by the time I upload it to YouTube we don't lose the resolution, that the volume of, or the size of the voxels determines the absolute resolution. So if you have bigger voxels, you get chunkier triangles, and very high resolution you get nice surfaces, but you'll get many more times voxels. So there's a trade-off somewhere. Typically we just get whatever data we're given, and you run the Marching Cubes and then you post-process it. You're normally not in control of the volume data. Also, I notice if I compute surface normals, maybe I'll put it on low resolution. If we compute normals, essentially, if each triangle in this surface has no normals, then the graphics system will apply a very primitive or very basic shading algorithm. It will just look at the surface. It will be able to, well, depending what settings you have, of course, it will typically have a surface normal per triangle, not per vertex. So if you imagine for each triangle you only know the surface normal in the middle, and then the graphics system doesn't attempt to interpolate the angle across the face of that triangle. When you compute the surface normals at each vertex and you store them, OpenGL knows therefore that it can interpolate these normals, so you get a nice smooth rendering even when you've got pretty poor resolution data. Now again, this is probably less of a concern when we've got very fast computers, but bearing in mind that for computer-aided surgery you're often trying to do things in real time, you might end up in a position where actually you need a fairly good rendering and you want as few, a very much reduced number of triangles. So if you end up in this position where you're getting blocky renderings, it probably means you've forgotten to compute the normals on a per vertex basis. Anyway, that's a bit of an aside. To explain how the Marching Cubes algorithm works, I won't go through all of the cases because there's 15 specific cases you have to consider in the original paper, and I think it's up to about 33 in later papers. But for the sake of explaining how the algorithm works, imagine you are simply iterating through voxels at a time. So you take a position in your volume and you look for the 8 voxel values or the intensity values at these sort of your neighbours. So I suppose it depends if you consider where your origin is, but essentially you just need 8 voxels next to each other arranged in a cube. If you consider if you're working based on the centers of cubes, you'll have a slightly different outlook on these things. But for the sake of this, if we imagine then that I'm looking for a threshold of 50, and obviously if all of the 8 neighbours are above 50 or all of the neighbours are below 50, then the threshold is not crossed in this group of 8 in this block of data. In other words, I don't need a triangle. So the marching cubes algorithm is only really interested in when you consider these 8 voxels and one or more of them is above or below, and the remaining are the other side of your threshold. So for example, if in this scenario I'm looking for threshold of 50, this red one here, this corner red one, could be above 50, so it's 100, and the remaining 7 are all below 50. So the red dot indicates above 50 and no dot indicates below 50. That means somewhere in this volume I have crossed the threshold that I'm looking for. So in this scenario, imagine there's 0 at the top here and 100 at the bottom, and you're looking for exactly 50. What you really do is you linearly interpolate along each edge. So in this case, the position that you're looking for is exactly halfway between the 0 and the 100. If you were looking for a lower threshold, nearer the 0, this green position would move up. And if you're looking for a higher value, it would obviously move down. So we linearly interpolate this edge. And obviously there's 100 here, but this other edge along here at the back goes down to 0. So similarly, we linearly interpolate along there. And likewise, we linearly interpolate along here. So given a threshold of 50, we have decided that a triangle could be placed here is where the threshold or this isosurface intersects these 8 voxels of data. I do hope that makes sense because it feels like I'm talking to myself. So just to consider a couple more cases, I've picked the simple ones that I can draw on a pen and paper. So again, if you imagine another block of data, these 2 are above the threshold, the remaining 6 are below, and you can see that we can identify these 4 points, and these define a surface representing the fact that the contour, the isosurface you're looking for, intersects and in this plane. And again, obviously I've drawn it really as a kind of rectangle, but as I said, you'd normally convert all these things at the end of the day to triangles, so you can just obviously subdivide it into a triangle. So typically triangles do draw quicker. Here's another one. So the 4 bottom ones are above the threshold, the 4 top ones are below the threshold, therefore the surface comes in the middle. So the marching cubes algorithm has a lookup table where you consider every single combination of above and below. I mean, if you want, you can go and draw them all. Don't forget, however, it's not every combination, because if you work on the basis of reflection or rotational symmetry, you can reduce the size of your lookup table. But essentially, there are a certain number of cases. If I quickly go to, I did have the original paper somewhere. Quickly, let's go to Wikipedia. So in the original article, for example, you'll see how there's a whole bunch of these different configurations, some of which are easy to draw and some of which are not. This one is an open source thing on Wikipedia. So the principle there is essentially then that we're going to iterate through our whole volume of data. For every block or every 8 neighborhood of voxels, you have to consider, are they all above the threshold? Are they all below the threshold? If so, I can skip it. If they're not, then I need to look up in my lookup table and work out where the best place to place my surface is, given the fact that I'm linearly interpolating along these edges. Now, obviously, from a pure computer science point of view, there's a lot that you can do to optimize that. Also, if you've got voxels next to each other, if you imagine it, you often don't want duplicate points, so you need to filter out duplicate points. So a nicely written algorithm, there's quite a lot more going on. But from the perspective of this course, this computer-aided surgery course, essentially all you need to know is that there are many cases that determine where you place your triangle, but the marching cubes algorithm is a deterministic way of just filtering through your data and outputting triangles at each voxel where necessary. The rest is pure kind of optimization and performance enhancements. So here you can again get the idea now that every time we change this threshold value, we're actually iterating through this whole volume of data and recomputing a different bunch of triangles. So it's quite amazing that it goes quite this quickly, but that's modern life for you. And again, on here now, you get the idea of, here I'm actually creating more voxels on the fly and remeshing them. But here, if I actually just change the threshold, so if you're wondering where those holes come to, obviously it iterates right to the edge of this cube. You can kind of see the outline of the cube now. And again, this button here to merge points or not. Obviously you won't really see the difference here because it'll look the same regardless. So I hope that gives you an overview of what the marching cubes algorithm does. It simply iterates through each block of 8 voxels, checks the corner intensities, decides if any one of those corners is traversing the threshold you're looking for, and if so, goes to a lookup table, works out which triangles it needs to implement, and it linearly interpolates along the edge. Thank you much.